Hello, today I'm going to be talking about gradient descent for linear regression. This is going to be a short video, and I've waited a while to think about what I want to say for this video because it's very important, right? So in linear regression, we have y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus dot 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 plus beta p minus 1 xp minus 1. If we have p minus 1 is our number of variables, p is the number of parameters, beta, and we can say n is our number of points, xi, yi, right? So we have multiple different x variables. So xi is a row of containing all of those variables, right? And like we're saying a specific row is labeled I, right? So we can say yi equals beta 0 plus beta 1 x I1. So that's the ith row and then the first variable. Right, and then I goes from 1 to n. That's often called the index or the row. It's the label for the point, right? And then we can put this in matrix form as y equals x times beta. And you're like, okay, well here we're obviously taking the x1 column and then multiplying it to beta 1, right? But here the what x is being multiplied. Well, we can think about having a column x0 that's just always ones, right? So x equals, our x matrix here equals ones, a column of ones for n times. So I'm just using this notation to show that we have a column of n ones. And then we have a column for x1, column for x2, all the way to our column for x p minus 1. And that means this matrix x is size n times p because we have n rows and p minus 1 columns. We have these p minus 1 variables plus 1 for the bias, right? And that's why I said our number of variables, we can call it p minus 1, so that when we talk about the number of parameters, including this bias term, like the y-intercept, that we get to p. And then over here, the dimensions work out, right? So this one's n by p, this one's p by 1, and this one's n by 1, our y data, right? So like x I0 equals 1 for all I in 1 to n, right? We just have xi0 is the 0th column and then the ith row. We could, like the way I'm talking about I, it's 1 to n indexing. You could also have it as 0, 1, 2, n minus 1 indexing. And like that's not really going to change anything else in the notation that I write. Um, mhm. And so after we decided this was the linear model y equals x beta, we looked at our objective, which was to minimize the loss of beta, which is the sum of squared error. So we chose sum of squared error as our loss function that we're minimizing. So sum from I equals 0 to n minus 1 of yi minus xi beta squared, right? And so again, I'm using the 0 indexing, and so we have y0 to yn minus 1 are our y values. Those are just scalars when we plug in the y, right? And then when we plug in the I, here we get the row, the ith row of this x matrix, right? So our x is going to be a big matrix, right? And we're just getting row number I. And then beta is already a p by 1 column vector, right? P by 1. And so each row is 1 by p, right? So after we do this computation, for each I, we're going to get a single value, square it, and then add them all together. We said we could write that in matrix notation as well, right? So L of beta equals y minus x beta 2, 2. So this means the 2 norm squared. So that's exactly the same as taking each element, squaring it, and then adding it all together. Same as the sum of squares. And then we said our solution to this was called beta hat, and it equaled xtx inverse xty. And so if we know the x matrix and know the y matrix, we can calculate the linear regression coefficients beta hat pretty simply, right? And then, but let's talk about more how we found this. So this is a direct method. We take x and y, the whole thing, and we plug it into this equation. This is going to involve a lot of computation, right? Because we have to multiply two matrices together. That involves addition and multiplication. And then we have to find an inverse, which is also computationally expensive. So perhaps there's another solution or way to get to the solution that is faster. And then we also want to think about, okay, well, our model y equals something and our loss function L of beta are pretty simple for linear regression. But for more complicated optimization problems, we'll want to have other methods besides the direct method, because we won't always be able to set the first derivative equal to 0 and have a concave second derivative. And sometimes first order optimization wouldn't necessarily be enough, or just like even doing that, we would want to use gradient descent, right? So gradient descent is the method besides the normal equations. So here's the normal equation. That's what we call the normal equation solutions, or specifically, like if we write it the other way, xtx beta hat equals xty, that's our normal equations. The other way is going to be called gradient descent. And for that, to derive the normal equations, we use the first derivative. And for gradient descent, we still need that derivative, right? So we said that dl d beta j equals -2 sum over I of yi minus xi beta, xij, right? So we're taking the derivative of this with respect to beta. We have to pull the 2 out front, pull the -1 out front, and then pull the xi to the side as well, right? Because of chain rule. And then when we're taking the jth beta, we're indexing it at index j, right? So like specifically when we said we want DLD beta 0, that was -2 sum I of y minus xi beta. So we still need that entire row xi to get our prediction y hat. It was xi beta, right? And then we need to multiply xij. For the 0th row, we're saying that xij, that's just, 0th column, that's our column of ones, right? So for the bias term, we're just multiplying 1 every time. For the first slope term, we're doing sum over I minus xi beta xi1. So it depends on that value in the first column of x. And again, if we want to write this in matrix or vector form, we can talk about the gradient of L of beta. Notation, we could also write it like this, like gradient with respect to beta of L. So beta is that vector, it's that p by 1 column vector of betas, right? But we can talk about the gradient as the DL beta as the vector of all the different DL beta j's, right? And p minus 1 is our last beta. And so we have negative 2 sum I yi minus xi beta xi. So here we were indexing it at j to get the jth beta. Now, no index j because we want the entire column, not just a single value, or entire row, I mean. Yeah, writing it this way, we get a row vector. Row vector. And as I've written it here, like, right, we're putting all these in a row. And then if we're expressing this in matrix notation, right, we can do negative 2 out front, and then we have the y minus x beta transpose times x, because this is going to be a 1 by n vector, and then this is going to be an n by p vector, and then our result is going to be 1 by p, right? So that's a row vector of length p for these derivatives. And let's think about writing it as a column vector too, right? So that would be just taking this transpose, right? So column vector is the transpose of this, right? So we want it to be p by 1. And we're just going to do y minus x beta transpose x, and then take the transpose. So we still have the negative 2 out front. And because y minus x beta is a row vector, it has that 1 out front, right? So, well, yeah, when we do the transpose. But if we just do it like this, then it's Rn by 1, right? N by 1 dimension. So if we skip a couple steps in the simplification, basically we're applying the transpose there and changing the order. So negative 2 xt y minus beta x. And this is a little helpful because we wrote beta as a p by 1 column vector, right? So now that's the same dimension as beta. But moving on, let's go to the gradient descent algorithm. And for that, instead of using a direct method as the normal equations do to find beta, we're using an iterative method. So we start with an initial guess for the solution, beta 0. We can initialize it to 0. And then we say, well, beta is not converged. Like, we can have some good conditions such as the norm of beta k plus 1 minus beta k is greater than some threshold, like cutoff for precision, right? So after one beta becomes super close to the next beta, we stop because we're not really changing our beta. We've hit that optimal beta to the number of decimal points that we care about, right? And so while we still want more decimal points and precision, right, we're going to keep doing the iteration, and that iteration is beta. So this is a vector, right? So really we're setting it equal to 0 being a vector of p zeros, right? This is right, 0. You could subscript p, or you could like think of it as 0 0 0 dot 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 0 transpose, or whatever you want. But basically, like, we have j as our index for each specific beta. So when we're doing the update at first, let's think about how do we update a specific beta j. So this right side, left side is saying that the k plus 1 iteration of beta what is the value for that? We're going to set it by taking the kth value for beta, the value for beta at iteration k. So this k superscript is our iteration number. That's why I put it in parentheses. We're not raising it to the power of that. We're just keeping track of what iteration we're at, and we're going from iteration k to iteration k plus 1 every time. And we're just going to take the old beta value, and then we have to subtract times gamma dl d beta j. And so gamma we haven't talked about before. This is a new parameter specific to gradient descent. It's called the learning rate. So whenever we do gradient descent, we have to choose a learning rate. And what does that mean? Well, it scales how big this step size is, right? If gamma is big, then our transition to beta k plus 1 is going to have a larger difference, right? If we have gamma equals 1, we're going to make a big step between each beta. If we have gamma equals 0.01, then we're going to make a tiny step between each beta. And that changes like how many iterations we need to get to the solution, but it could also change what solution we get at, not in the linear regression case, but in the other case where we have a non-concave function and we have multiple local extrema, right? So as we said, this using the gradient descent method, we're going to get to a local extrema. The next maximum minimum critical point in the loss function, right? And since linear regression is concave, our loss function is quadratic, our first derivative is linear. So we always reach that optimal solution. For linear regression, even with gradient descent, we're always going to reach that exact same single optimal solution every time. But if we have a very complicated optimization problem and we're approximating the solution, then it does matter what we choose gamma. But right now, don't worry too much about gamma. We could just have it be 1 for linear regression. And then beta k plus 1 would be writing this back into vector form. So this beta represents all the beta j's. That's going to be beta k minus gamma dl d beta. So that represents all the betas. Or we could even, let's write it in this form since that's a little easier to see how that's a vector, right? And then we want to substitute in what this vector is for linear regression specifically, right? So this is for all gradient descent when we have the loss function L of beta. And now we want to substitute in our specific grad L beta, which right up here, if we write it in row form, but since I've written this as a column form, right, we'll use the column form of it. So this guy, substituting that in, the negative times the negative becomes a positive 2 times gamma times xt y minus beta x. Wait, I wrote beta x. I mean, that's a mistake. It should be x beta or beta t xt. X beta. X beta. There we go. In addition to the regular gradient descent algorithm, also called the steepest descent, since we're using the entire gradient, right? We can look at stochastic gradient descent. Stochastic means probabilistic or random. So instead of straightforward doing the gradient on the entire data set, we're going to introduce some randomness to possibly end up with a different solution. Although, as I said, in linear regression, it's concave. We're always going to have the same single optimal solution no matter what. When we have other loss functions, stochastic gradient descent might produce a different result, and it would often be a better result when it's different, because it's not like focused around this initial solution, right? So anyways, we introduce our loss function L of beta, let's just copy that being the same, or from 0 to n minus 1, whatever, of y I minus xi beta squared, right? And then now we're looking at the loss function for a specific point, a specific row I, right? So instead of summing over the entire data set, we're just going to take the squared error at a single row. And then instead of using the entire data set, it now depends on which I is selected, right? So first we can initialize beta 0, and instead of setting it equal to 0, it's better to do a random initial value, because then our solution could be further away from 0, right? We're not going to get the local extremum that's close to 0. It's going to be close to some random value. And while beta is not converged, the same condition, right? We're going to choose I as a random index and then update beta using the gradient on this single point, right? Not the entire data set. So k plus 1 is going to be updated by doing beta k and then minus the learning rate is still there. Gradient of Li of beta, right? We could also write that as dLi d beta. And then again, that's the general form for all stochastic gradient descent. And then over here, we plugged in the specific loss function for linear regression, which was sum of squared error, given the y equals x beta model, right? So here we can do the same thing. We're going to get, but instead of the matrix, right, we're just dealing with a single row. So like this thing up here without the summation, plus 2 gamma yi minus xi beta xi. And so, like you're saying, how is that going to get us to the same solution? Well, if we do it many more times, we're going to have to increase k more times than with regular gradient descent. But eventually, we're going to get to that same optimal beta. Like, even though we're going through many more iterations, each iteration is way fewer computations. To get the gradient, we just have to do one vector times vector multiplication, and then scalar minus scalar, then scalar times vector. But this vector is just, right, the p by 1 vector to update the p by 1 betas, right? For each beta j, it's actually just one vector multiplication, and we're right, doing 1 by p and p by 1. That's really just p multiplications and p minus 1 additions, the dot product. Right, so it's very fast to do a single integration in stochastic gradient descent, versus up here, this thing is not very fast. There's going to be a lot more cross product terms. And not only is it a lot faster, it's also random which I we choose, right? We're not going over the entire data set, taking basically, like in gradient descent, we would be basically taking the same direction every time. For this k, 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 we're going in the same direction, right? But now our direction depends on what's I is chosen. So we're kind of taking a more indirect path to get to the same solution. Not only is it indirect, like I also said, there's a lot more iterations. So these arrows are a lot smaller. And So maybe we don't need as small of a learning rate. And like the only reason you would want to make small steps is so that you don't overstep the solution and have to come backwards, right? If we took an arrow like this past the optimal solution, then we would need to take another little arrow like that to get to the optimal solution.